Hi, I'm Brent Zoomers, and in this video I will present our work, PRoGS, Progressive Rendering of Gaussian Splatting. First, let's review the basis of 3D Gaussian Splatting. 3D Gaussian Splatting is an approach that, given a set of post images taken within a scene, allows the visualization of novel viewpoints using 3D Gaussians. These Gaussians are mathematical objects defined by parameters, their position in space, their shape, orientation, opacity, and their color. These are then optimized to capture the visual information of the scene based on a set of post images provided during training. To improve the representation, Gaussians can be cloned or split during optimization, dynamically adapting to the scene's details. Once optimized, they can be rasterized to any viewpoint within the scene to get a rendered image. To calculate the color of a pixel, the Gaussians are first sorted front to back. We then calculate the color by considering the opacity and color of that Gaussian and the transmittance thus far. Transmittance reflects how much power Gaussians have already contributed to that pixel's value. Despite this technique achieving great results, it takes up a lot of memory for large scenes, which results in slow loading times. One solution is to send chunks of splats, but this does not guarantee that the most critical parts of a scene are loaded in first. The online viewer by any matter determines an ordering among splats based on the combination of scale and opacity, which does not necessarily focus on important parts of the scene. We propose PRoGS, which focuses on loading relevant splats first. By taking into account the contribution of Gaussians during rendering, we can create an ordering based on their contribution to the scene. To calculate the contribution, we again look at the different elements that play a role in coloring a pixel. By taking into account these different elements, we can determine the final ordering as the sum of the contribution of each Gaussian to each individual pixel across training views. This little toy example will explain the intuition behind this more clearly. By calculating contribution as a sum across camera views, we inherently prioritize Gaussians that appear in multiple training images. In this toy example, a large blue object is visible in all training views, and the green object is including the yellow and black objects in the back, with the black one being more visible than the other. This results in the ordering on the right. This, however, portrays only one possible scene composition. To argue each aspect of our approach, we will divide scenes into one of three categories. First off, we have the inward-facing scenes, with some center of importance. Secondly, we have forward-facing scenes, where the complete scene can be considered important. And lastly, we have outward-facing scenes, where importance is very spread out and no single object is considered more important than the others. Each type of scene has different properties that are important to consider when determining contribution. Forward-facing scenes are the simplest, as most splats appear in most images, and thus can be represented well by the sum of contribution. The other examples, however, are not so easy and require some extra attention. This image on the left, for example, of an inward-facing scene, shows that we indeed allow the center object, in this case the bicycle, to be reconstructed well. The background, however, shows significant artifacts negatively impacting perception. On the right, we have an outward-facing scene where contribution is spread throughout the scene and the whole scene suffers in quality. To allow our approach to shift focus to include parts of the background where necessary, but still mainly focus on important objects, we use an octree structure to guide the selection of Gaussians throughout the scene. Without octree, the highest contributing splats will mainly be focused around the center. Using the octree allows us to spread out Gaussians while still prioritizing the densest parts of a scene. To determine the ordering, we take a percentage of splats per cell and repeat this until all splats have been selected once. Putting the results side by side, we clearly see the impact using an octree has. These example images illustrate this further as we see the background gets significantly better while the foreground takes a small hit in quality. The depth of the octree has a significant impact on the quality of the render, as setting the depth too low or too high results in the Gaussians not being spread out enough. In this example, the first and last images clearly show artifacts of under-reconstruction. Using a depth of 3 has shown to work well in these test scenes. Another benefit we get for free by using an octree is the use of frustum culling, allowing us to only send Gaussians that are currently in view. Frustum culling also helps with outward-facing scenes as we can focus on retrieving important splats currently in the view. We perform frustum culling using the mean of the Gaussians and treating it like a regular point cloud, where points within view are included in the priority list. In this example image, we show the impact of each separate addition. Notice how frustum culling and the use of an octree complement each other well to achieve the best metric score. This is also reflected in the metrics, where we consistently outperform our competitors across all scenes and metrics. We want to point out that we focus especially on the earlier percentages, as in the end, all approaches will converge to perfect reconstruction of the original scene when all splats are sent. So far, we have considered our approach at a scene level. The principles used, however, can be transferred to singular objects without any changes. We can segment out objects in a scene and calculate the contribution of splats within that object to determine important splats. As for a singular object there is no background, we do not use an octree in this case. We see potential in using a combination of both scene and object level contribution to dynamically retrieve Gaussians, but we leave this as future work for now. Another advantage of our approach is that it does not rely on implementation-specific information. Any 3D.js-inspired approach that uses explicit primitives and stores per primitive information can apply our approach to determine an ordering. We tested our approach using compressed 3D Gaussians for accelerated novel use synthesis and showed that our results hold up. In this example, we render 10% of the splats using both our method and the antimatter viewer method, and we see that the same observation can be made as before. As they state compression rates of up to a factor of 31, combining our approaches can allow representative visualization of a scene using around 300 times less data than the original approach. To conclude, our approach allows progressive rendering and streaming of 3D Gaussian splatting scenes by determining an ordering among splats based on their contribution to the training views. This works both at a scene level and object level and can be used together with existing compression approaches to drastically reduce the amount of data needed to render initial versions of a scene. If you have any questions about our work, or you want to discuss something about it, don't hesitate to reach out through email or LinkedIn. Thank you for your attention.